In this video, I'll go over the different distributions and all of the different hypothesis tests and confidence intervals that your calculator can do. First, let's look at the distributions. So I'm going to second vars. And this is where the normal distribution lives and the t-distribution. And this can actually eliminate your need to use the t-table or the normal distribution table or even the chi-squared table. So as we look at these, we have the normal distributions are the first three, the t-distribution is the next three, and then we have chi-squared. One note, if you have a TI-83, then the inverse t function will not be on there, so you will have one less t-distribution that you're working with. Okay, so in each of these we have a PDF and a CDF. And the PDF is something that we never want to use. The PDF is telling us the Y value for a particular X value, which is not actually useful. We want to use the CDF in each case because that's going to tell us the area under the curve. So if we use the normal CDF, that's going to tell us area under the curve of a normal distribution. And we need a lower bound and an upper bound, and then a mean and a standard deviation for this. If you've turned everything into a z-score, then you can leave your mean and standard deviation as 0 and 1, because that's the standard normal curve. If you, for instance, had done a hypothesis test and found that your test statistic was 2.6, and you wanted the probability that your test statistic was greater than 2.6, then your lower bound is going to be 2.6 and your upper bound is going to be some big number, just to call it 1,000, and then go to paste. If you're using a TI-83, you're going to be doing the exact same thing that I'm doing here, except for do lower bound, comma, upper bound, and then press enter. And so we get paste here, and enter. So this is telling us that 0.004 is the area in the normal distribution to the right of 2.6. This should be, if you did this on the normal distribution table, you would get 1 minus that answer. You would be getting, when you looked up 2.6 in the normal distribution table, you would be getting 0.995 because the normal distribution table is telling you area to the left. What we just did up here was telling us the area to the right. If we go back to second vars, then we've talked about normal CDF. Inverse norm is telling us if I give it a probability, it's going to give me the corresponding z value. So this would be, if I'm looking at my normal distribution table, this would be like I start out looking in the inside of the table and I'm looking for the corresponding z value. This is useful when you're trying to calculate critical values for a confidence interval. So if I'm doing a 98% confidence interval, that means 98% of the data lives in the middle and 1% lives in each tail. So if I type in 0.01 corresponding to 1% in the left-hand tail and press paste, this is going to give me that the critical value for a 98% confidence interval is 2.33. The negative doesn't actually matter here because it's a confidence interval and we have that plus or minus. Okay. This would also, inverse norm also works when you're talking about percentiles. This is the z-score, keeping it negative here. This is the z-score for the 1 percentile. So this would be the z-score for somebody in the percentile where only 1% of the people are below them. Now we can look at the t-distributions. Inverse t works the same way inverse norm did. It's going to give us a t value corresponding to a particular area. Once again, you can use this to find critical values for t distributions. So maybe we'll do 0.01 again for a 98% confidence interval. I don't know. We'll make up a degrees of freedom as 9, and we paste and press enter. This is telling me if I'm working with a 98% confidence interval and 9 degrees of freedom, my critical value is 2.82, which hopefully should match what you would find on the t-distribution table. If we keep going, once again, T-PDF we're not going to use. T-CDF works in the same way that normal CDF does. It's going to tell me area under the curve of the T distribution. So once again, we give it a lower bound and an upper bound. If I find a test statistic of negative 1.23, and I want to find the probability that T is less than that particular value, then my lower bound is just some small number. Negative 1 times 10 to the 99th works. You could also use negative 10,000 or something like that. We need some degrees of freedom. We'll keep it at 9. This would depend on your problem, and press paste. And so this is giving me my p-value. This is the probability that T is less than negative 1.23 if we're working with 9 degrees of freedom. And finally, under the distributions, we can look at the chi-squared CDF. We're going to skip the chi-squared PDF again. And this is going to tell us the area under a chi-squared curve. When we're working with chi-squared distributions, we're always looking for area to the right. So the value you get from chi-squared is always going to be your lower bound. Let's maybe make that 2.3. My upper bound, once again, a very big number. The degrees of freedom, remember, is coming based on what you're working with. That was either, if you're working with a chi-squared goodness of fit, that's the number of categories minus 1. Or if you're working with either of the two other chi-squared tests, that's the number of columns minus 1 times the number of rows minus 1. So let's just say our degrees of freedom here is 9. And so the area to the right of 2.3 in a chi-squared distribution with 9 degrees of freedom is 0.9857. Okay? So all of those distributions will help you if you are either trying to find a critical value for a confidence interval, if you're trying to find probability under a normal distribution curve like we did last semester, or if you're trying to calculate a p-value once you've already calculated a test statistic. And now we can go and look at the hypothesis test and confidence intervals, and those are going to live where the list lives, so just under stats and over to test. And this has our long list of different tests. I'm going to go through some of these fairly quickly, and you can ask me questions if you have more. Anything that just does not say proportion in it is dealing with means. So like all of these first 4 don't say anything about proportions. So those are referring to means. The ones that say proportions are dealing with proportions in particular. The z-test for means we would only use if we know the population standard deviation, which we almost never know. So you're probably never going to use number 1, number 3, number 5. Oh, wait, sorry, number 5 is a proportion, that's okay. Number 7 you wouldn't use, or number 9. So those are all ones that are z intervals for means, and we would only use those if we know the population mean. So the ones that you would use a t-test. That's if you have a single mean and you're doing a hypothesis test. The 2-sample t-test is if you have 2 means and you're doing a hypothesis test. The proportions, so we have the 1 proportion and 2 proportion test. That's if number 5 is if I have 1 population and I'm doing a hypothesis test for proportions. Number 6 is if I have 2 populations and I'm doing a hypothesis test for proportions. The t-interval is if I'm doing a confidence interval for a single mean. The 2-sample z-interval, like I said, is one that you won't use because we would need to know the population standard deviations in that case. The 2-sample t-interval, that's if I have 2 populations and I'm working with means and I want a confidence interval. 1 proportion z-interval, that's if I have 1 sample and I want a confidence interval for proportions. 2 proportion z-interval, 2 samples for proportions. And then we have our chi-squared test down here. So the chi-squared GOF test, that's the goodness of fit test. And if we look at that, what this wants us to tell us is it wants the observed list and the expected list. And then it wants us to tell it the degrees of freedom. So let's see if my list, the ones that I have in there right now are not going to work. I went ahead and paused the video and put some data in my list that would actually work here. So I made my observed list, list 1, my expected list, list 2. This is kind of like the example where the accidents outside of a school where we were expecting an equal distribution across days. So we had 20 as our expected value. And so now if we go back to stat and test and we look for that chi-squared goodness of fit, then with list 1 as our observed values, list 2 as our expected values, the degrees of freedom here is actually 4 because we had 5 categories, and that should be n minus 1. We press calculate, and so this gives us both our chi-squared and our p-value here. This down here, this contribution, this is telling us the contribution to chi-squared for each of the terms. If we add all these numbers up, we should be getting chi-squared. And so what we're noticing here is that that fourth entry is contributing the most to chi-squared. So that was the value that was most different from what we expected it to be. And the other chi-squared test are both under the just chi-squared test. That will give you both the chi-squared test for homogeneity and for association and independence. And if we look at that, it actually wants matrices in here. So to get to the matrices, you go to second X inverse and go over to edit. And what you're going to do here is you're going to enter your data into a matrix. So let's suppose that we have a, 2 by 3 table. So we have 2 rows and 3 columns. You are not, if your table has like the totals in it, do not enter the totals into this matrix. Just enter the data from the middle of the table. So I'm just going to make up data here and hope that this works for us. Okay. And so now if we go back to our chi-squared, looking for number C there, and we've given it our observed matrix. We do not actually have to give it our expected matrix. It's just telling us where it's going to store the information. And we can go down to calculate. So it's given us our chi-squared value, that's our test statistic, our p-value, and it's actually calculated our degrees of freedom for us. That makes sense as our degrees of freedom because we had 3 columns and 2 rows. So we should have 3 minus 1 times 2 minus 1 as our degrees of freedom, which is 2. And if we go back and look at our matrices, matrix B actually has stuff in it now. And so if I press enter and enter, this is matrix B. This is the expected matrix. So we are actually looking at our expected values right now. We can see that we have an expected count of less than 5, so we actually, our conditions were not met here. If we scroll over, we can see we have several, we have another 2 values that were less than 5. So we should actually not be doing a chi-squared test with the data that I typed in there. There's a few more tests under the hypothesis test here. These are not ones that we're going to use, so you do not need to worry about those.